China is building a Ghost, a new stealth bomber, the H-20, designed to be undetectable and unstoppable. It is Beijing's answer to America's B-2 Spirit and B-21 Raider, a weapon intended to project Chinese power across the globe and complete its nuclear triad. But separating fact from fiction is the ultimate challenge. While Chinese officials claim there are no technical bottlenecks, U.S. intelligence remains skeptical, suggesting a truly operational bomber is still years, perhaps a decade, away. So, what is the H-20? A paper tiger or the phantom that will finally challenge American air supremacy? Its ultimate effectiveness remains contingent upon surmounting significant technological and systemic hurdles, particularly in developing high-performance engines, durable stealth materials, and the complex operational network required to support such a weapon. The development of the H-20 is not a standalone technological endeavor, but the logical culmination of China's evolving military doctrine, national ambitions, and specific strategic requirements. It represents the final and most technologically demanding component of the PRC's pursuit of a comprehensive, modern military capable of projecting power far beyond its borders. For decades, the PLAF was a force configured primarily for territorial air defense and limited regional operations. Its bomber fleet, consisting of variants of the Xi'an H-6, itself a derivative of the 1950s-era Soviet Tupolev Tu-16, lacked the range, survivability, and payload to constitute a true strategic threat. Under the military modernization drive directed by President Xi Jinping, the PLAF has been tasked with transforming into a force capable of projecting power globally, in line with China's ambition to become a world-class military. The H-20 is the central pillar of this transformation. It is designed to be a reusable, penetrating strike asset that provides capabilities fundamentally different from the PLA rocket force's ballistic and cruise missiles. Unlike a missile, a bomber can be recalled, redeployed, and used as a flexible instrument of statecraft, providing a persistent threat that complicates enemy defenses. A robust nuclear deterrent is traditionally built upon a triad of delivery systems: land-based intercontinental ballistic missiles, sea-based submarine-launched ballistic missiles, and air-breathing bombers. Each leg possesses unique attributes that enhance overall strategic stability and survivability. While China has long possessed land-based missiles and has a maturing sea-based deterrent, it has lacked a credible air-breathing component. The H-20 is explicitly designed to fill this gap. A stealth bomber provides distinct advantages. It is highly survivable against a preemptive first strike due to its ability to be dispersed and kept on airborne alert. It offers unique signaling options during a crisis, where its forward deployment can convey resolve without crossing the threshold of a missile launch. And it provides a flexible delivery platform for a variety of nuclear payloads. Official PRC state media and U.S. intelligence reports have both confirmed the H-20's designated nuclear mission, cementing its role as the capstone of China's strategic deterrent posture. The H-20's development has been a long-term project, marked by deliberate secrecy, punctuated by carefully managed releases of information. Development is understood to date back to at least the early 2000s under the leadership of the Xi'an Aircraft Industrial Corporation, a subsidiary of the state-owned Aviation Industry Corporation of China. The program was first publicly acknowledged in September 2016, when then PLAF Commander General Ma Xiaotian announced that China was developing a new generation long-range bomber. AVIC and the PLAF released promotional videos in 2018 and 2021 that concluded with brief glimpses of a large, flying wing aircraft concealed under a sheet. This controlled messaging strategy generated significant international speculation while revealing no concrete details, mirroring Northrop Grumman's own early marketing for the B-21 Raider. In March 2024, PLAF Deputy Commander Lieutenant General Wang Wei stated that the H-20 would be revealed very soon and that the program faced no technical bottleneck. This optimistic projection stands in stark contrast to U.S. intelligence assessments from late 2024 and early 2025, which consistently project that the H-20 is unlikely to achieve meaningful operational capability until sometime in the next decade or the 2030s. During this period, unconfirmed, grainy images purporting to show the H-20 in flight began circulating on Chinese social media. This persistent and significant divergence between Chinese official pronouncements and U.S. intelligence assessments is likely not accidental, but rather indicative of a deliberate information strategy. The claim of no bottleneck is highly improbable for a program of this complexity, particularly given China's well-documented historical challenges with advanced aero engine development. By creating the perception of an imminent and highly capable platform, Beijing can achieve deterrent effects long before the H-20 is fielded in significant numbers. This forces potential adversaries to begin planning and allocating resources to counter a threat that, for the moment, exists more on paper than on the flight line. This approach aligns with the characterization of the H-20 as a phantom bomber, a strategic tool whose primary value is currently derived from its potential complicating adversary calculations and serving as a powerful symbol of China's technological progress. An assessment of the H-20's potential capabilities begins with a technical analysis of its physical design, materials, and propulsion systems. While definitive specifications remain classified, a consistent picture has emerged from intelligence assessments, analytical models, and official Chinese media teasers. The H-20 is universally assessed to be a subsonic, flying-wing heavy bomber, a design that is broadly analogous to the American B-2 Spirit and B-21 Raider. This configuration is considered optimal for achieving all-aspect, broadband low observability. The absence of vertical and horizontal tail surfaces and the smooth blending of the wing and fuselage eliminate many of the sharp edges and right angles that are primary sources of radar reflection. This makes the aircraft particularly effective at evading detection by low-frequency early warning radars, which can often detect smaller stealth fighters with prominent tail surfaces. However, some evidence derived from wind tunnel models and unverified imagery suggests potential deviations from a pure flying wing planform. These include features such as a cranked kite wing shape, serrated air intakes, and most notably, foldable twin tail surfaces that can reportedly switch between a horizontal and V-tail configuration. The inclusion of any form of tail surface is a critical design choice. A pure flying wing is inherently unstable and demands an exceptionally mature and reliable digital fly-by-wire flight control system to maintain stable flight. The inclusion of tail surfaces, even if adaptable, provides a degree of natural aerodynamic stability which can simplify the requirements for the flight control software. Therefore, if the final H-20 design incorporates tails, it may indicate a deliberate engineering trade-off, sacrificing a degree of low observability for reduced risk and greater control authority, perhaps signaling a lack of complete confidence in mastering the complex flight dynamics of a pure flying wing. Achieving a low observable profile depends critically on the use of advanced materials and coatings designed to absorb and deflect radar energy. The H-20's large surface area will require the mass production of durable, weather-resistant, and easily maintainable radar-absorbent materials. Recent unclassified research from Chinese institutions indicates significant progress in this field. A team at Peking University, for instance, has developed a flexible graphene at silica fiber membrane just 0.1 millimeters thick that can withstand temperatures of up to 1,000 degrees Celsius while reducing radar reflection to -42 decibels. Such a material would be ideal for managing the extreme heat generated by engine exhausts and aerodynamic friction on a high subsonic bomber, a critical component of reducing its infrared signature. Despite these advances, China is generally considered to be lagging behind the United States in low observable technology. The radar cross-section of its J-20 stealth fighter is assessed to be significantly larger than that of the F-22 or F-35. U.S. intelligence officials have publicly stated that the H-20's design is probably nowhere near as good as U.S. low observable platforms. While the H-20's flying wing shape will inherently give it a much lower radar cross-section than any conventional aircraft, it is unlikely to achieve the extreme level of all-spectrum stealth projected for the B-21 Raider, which benefits from an additional generation of U.S. research in materials science, signature management, and precision manufacturing. Propulsion remains the single most significant technical hurdle and pacing item for the H-20 program. China has historically struggled to develop and mass-produce reliable, high-performance military jet engines, often relying on Russian imports or reverse-engineered designs. The most probable engine for the H-20 is the indigenous Shenyang WS-20. This is a high-bypass turbofan originally developed for the Y-20 strategic transport aircraft with a thrust rating in the range of 138 to 140 kilonewtons or approximately 31,000 pounds force. Its high-bypass design is optimized for fuel efficiency at subsonic speeds over long distances, making it well-suited for a strategic bomber's mission profile. However, the selection of a high-bypass turbofan creates a fundamental conflict with the requirements of a stealth aircraft. High-bypass engines are physically larger in diameter than the low-bypass engines used in fighter jets. This necessitates larger air intakes and exhaust nozzles, which are exceptionally difficult to shield from radar. To prevent radar waves from reflecting off the highly visible engine fan blades, the H-20 will require deep, S-shaped serpentine ducts treated with radar-absorbent materials. Furthermore, the engine's thermal and acoustic signatures must be extensively suppressed to reduce the risk of infrared and sound-based detection. The ability of Chinese engineers to successfully integrate 4 large WS-20 engines into a low observable airframe will be a definitive test of the program's maturity and a key indicator of the aircraft's true stealth capabilities. The central question regarding the H-20's strategic impact revolves around its weapon systems and its ability to deliver a decisive payload against defended targets. Its strike power is a function of its payload capacity, the types of munitions it can carry, and its survivability en route to the target. Analysis of the H-20's payload capacity is complicated by widely divergent estimates. U.S. government sources, including the Department of Defense and the RAND Corporation, provide a conservative baseline figure of at least 10 tons. This figure is often cited as the minimum requirement for a strategic bomber mission. In contrast, numerous other defense analyses and media reports suggest a much higher maximum payload, with some speculating a capacity of up to 45 tons. These figures are not necessarily contradictory. Instead, they likely reflect a design philosophy centered on mission duality, allowing the aircraft to be configured for different operational scenarios. A long-range, deep-penetration strategic mission, such as one targeting the continental United States, would demand a maximum fuel load, thereby restricting the weapon's payload to the 10 to 15-ton class. This is consistent with the projected payload of the U.S. B-21 Raider, which is approximately 13.6 tons or 30,000 pounds. Conversely, a shorter-range regional mission, such as launching a large salvo of standoff cruise missiles against targets in the second island chain from the relative safety of Chinese-controlled airspace, would allow for a significant reduction in fuel in exchange for a much heavier ordnance load. The speculative 45-ton figure reflects this missile truck role. If achievable, this would make the H-20 one of the most heavily armed bombers in the world, on paper. To quantify how many tons of nuclear weapons the H-20 can carry, it is necessary to analyze its most likely delivery system, the CJ-20 air-launched cruise missile. Employing a standoff air-launched cruise missile is the standard doctrine for modern bombers, as it allows the launch platform to remain outside the densest rings of enemy air defenses. The CJ-20, also designated DH-20, is the air-launched variant of the CJ-10 land attack cruise missile and is confirmed to have a nuclear-capable version. The ground-launched CJ-10 weighs approximately 2.5 tons, and the CJ-20 is assumed to have a similar mass. The CJ-10 family carries a conventional payload of 400 to 500 kilograms, and a nuclear warhead is assumed to have a comparable mass of approximately 400 kilograms or 0.4 tons, consistent with modern warhead miniaturization efforts. While the exact yield is unconfirmed, analysis of its predecessor suggests a variable yield in the range of 20 to 90 kilotons per warhead. Based on these specifications, a payload capacity of 10 to 15 tons would allow the H-20 to carry between 4 and 6 CJ-20 missiles. A 6-missile loadout is consistent with the capacity of the current H-6K bomber and represents the most probable configuration for a full strategic strike. This corresponds to a total nuclear warhead tonnage of 1.6 tons for a 4-missile loadout and 2.4 tons for a 6-missile loadout. The total deliverable yield would be 80 to 360 kilotons for 4 missiles and 120 to 540 kilotons for 6. In its conventional role, the H-20 will serve as a launch platform for a diverse array of standoff munitions designed to dismantle an adversary's air defenses and strike high-value targets. In addition to the conventional variant of the CJ-20 air-launched cruise missile, which has a range of 1,500 to 2,500 kilometers, the H-20 is a logical future carrier for China's burgeoning arsenal of hypersonic weapons. A prime candidate for integration is the YJ-21, also known as KD-21, an air-launched anti-ship ballistic missile. This weapon is reported to have a range of approximately 1,500 kilometers and can achieve speeds of up to Mach 10 during its terminal phase, making it exceptionally difficult to intercept. An H-6K bomber has already been photographed carrying 4 YJ-21s, a loadout that would be well within the H-20's capacity. The H-20's true strike power is not merely a measure of its payload, but an integrated assessment of its range, survivability, and the advanced capabilities of its munitions. Its strategic value lies in its ability to credibly threaten high-value, heavily defended targets throughout the Indo-Pacific that are currently beyond the effective reach of less survivable platforms. By presenting a penetrating threat from multiple, unpredictable vectors, the H-20 can hold at risk key U.S. and Allied military installations in the second island chain, including bases in Guam and Japan, thereby strengthening China's anti-access area denial strategy. The Xi'an H-20 enters a highly exclusive domain of military aviation, with its only direct analogs being the United States Northrop Grumman B-2 Spirit and B-21 Raider. A comparative analysis of these 3 platforms reveals differing design philosophies, technological generations, and strategic priorities. The B-2 Spirit is the benchmark against which the H-20 will inevitably be measured. The B-2's primary advantage is that its capabilities are proven through decades of operational service and combat deployment in contested environments like Kosovo and Iraq. Its stealth performance, while dating to the 1980s, is a known quantity that has been continually updated. The U.S. possesses a mature global ecosystem to support B-2 operations, including experienced crews and a vast aerial refueling infrastructure. On paper, the H-20 may hold several advantages. As a newer design, it is expected to incorporate more modern avionics, sensors, and potentially broadband stealth technologies that reduce its signature across a wider range of sensor spectrums. Its speculative maximum payload of 45 tons would dwarf the B-2's 18-ton or 40,000 pounds capacity, and its projected maximum range of up to 15,000 kilometers could surpass the B-2's 11,100 kilometer range. However, all of the H-20's purported advantages remain theoretical until the aircraft is fielded and its performance can be independently verified. The B-21 Raider represents the next generation of American stealth bomber technology and is a more direct peer competitor to the H-20. The two aircraft appear to embody different design priorities. The B-21 is designed for affordability, survivability, and adaptability. With a smaller airframe and a payload of approximately 13.6 tons or 30,000 pounds, the B-21 prioritizes extreme stealth and operational range over raw carrying capacity. Its low observability is considered a generational leap beyond the B-2, incorporating advanced materials and signature management across the infrared, acoustic, and electronic spectrums, likely resulting in a significantly lower radar cross-section than the H-20. A crucial advantage for the B-21 is its open systems architecture, which allows for rapid and cost-effective integration of new software, sensors, and weapon systems as threats evolve. This ensures the platform's relevance for decades. The H-20, if it achieves its high-end payload estimates, will be able to carry a much larger volume of ordnance than the B-21, but likely at the expense of stealth and unrefueled range. The U.S. strategy with the B-21 focuses on fielding a large fleet of at least 100 highly survivable, adaptable aircraft, whereas China's production numbers and ultimate fleet size for the H-20 remain unknown. A truly effective strategic bomber force is a system of systems, where the aircraft itself is only one component of a complex operational and logistical network. The development of this supporting ecosystem represents a challenge for the PLAF that is arguably as great as building the H-20 itself. A stealth bomber does not operate in isolation. To find and engage targets, particularly mobile ones, at intercontinental ranges, the H-20 will depend on a robust command, control, communications, computers, intelligence, surveillance, and reconnaissance network. This includes a constellation of space-based sensors, over-the-horizon radars, and data fusion centers capable of passing target-quality data to the bomber via secure, low probability of intercept data links. Furthermore, achieving the H-20's full potential for global reach is entirely dependent on aerial refueling. This remains a significant and acknowledged weakness for the PLAAF. While China's fleet of Y-20U tankers is growing, it lacks the numbers, experience, and global basing infrastructure required to support sustained, dispersed bomber operations in a contested environment on the scale routinely practiced by the U.S. Air Force. Beyond the supporting technology, the PLAF faces significant human and logistical hurdles. The U.S. Air Force has accumulated decades of institutional knowledge in conducting very long-duration bomber missions, a level of experience the PLAF is only beginning to develop. This includes complex mission planning, multi-aircraft and multi-tanker choreography, and crew endurance management for flights that can exceed 30 hours. The sustainment of a low observable fleet is also exceptionally demanding. The specialized coatings and materials that give stealth aircraft their properties are often fragile and require meticulous maintenance in climate-controlled facilities to preserve their effectiveness. Establishing the extensive logistical tail of specialized hangars, depots, and highly trained maintenance personnel is a massive undertaking that is as critical to the bomber's readiness as the initial production. The immense requirements of the H-20 program will inevitably act as a forcing function for the broader modernization of the PLAF. To make the bomber a viable weapon system, the PLAF must address its tanker shortfall, mature its command and control architecture, and develop a new generation of aircrews and planners skilled in long-range strategic operations. Therefore, observing the growth of China's tanker fleet and the increasing complexity of its long-range training exercises will serve as key leading indicators of the H-20's true operational maturity. The introduction of the H-20, even in limited numbers, will have profound and lasting effects on the strategic balance in the Indo-Pacific and beyond. Its long-term impact will be shaped by its modernization potential and the geopolitical response it elicits from the United States and its allies. The initial operational version of the H-20 will not be its final form. Like all modern military platforms, it will likely be developed in iterative blocks, with capabilities enhanced over its service life. Future upgrades are expected to focus on several key areas, including propulsion, with the integration of more advanced engines, potentially incorporating variable cycle technology to improve fuel efficiency, range, and thermal signature management. Avionics and sensors will see continuous upgrades to its radar, electronic warfare suites, and sensor fusion capabilities, potentially incorporating artificial intelligence to aid in mission planning, threat detection, and autonomous decision-making. Weapon systems will be upgraded to integrate next-generation munitions as they become available, including more advanced hypersonic cruise missiles, directed energy weapons, and potentially serving as a mothership for launching and controlling swarms of unmanned combat aerial vehicles. A credible, deployed H-20 fleet will fundamentally alter the security calculus for the United States and its allies in the Indo-Pacific. The bomber's combination of range and stealth will hold at risk previously secure rear area bases, logistical hubs, and naval assets, particularly those on Guam and potentially as far as Hawaii. This capability serves as a powerful enhancement to China's existing anti-access area denial strategy, creating a multi-domain, multi-axis threat that is significantly more challenging to defend against. The presence of the H-20 will compel the U.S. and its partners to make substantial new investments in hardened shelters, force dispersal, integrated air and missile defense, and long-range counter-air capabilities, thereby increasing the strategic and financial costs of maintaining a credible forward military presence in the region. The Xi'an H-20 program faces immense technical, operational, and logistical challenges. The most speculative high-end performance claims should be treated with considerable skepticism until independently verified. Nevertheless, the H-20 represents the final and most ambitious piece in China's decades-long quest to build a military that can challenge the United States at a strategic level. The H-20 is not a silver bullet that will erase American military advantages overnight. However, should China successfully resolve the critical challenges related to its engines, low observable materials, and the creation of a comprehensive operational ecosystem, the bomber will mature into a true campaign-shaping platform. It will provide Beijing with a flexible and survivable intercontinental strike capability that solidifies its nuclear triad and fundamentally alters the balance of power in the Indo-Pacific. The transition of the H-20 from a phantom bomber used for strategic signaling to a real, operational, and proficiently crewed force will be one of the most critical military developments